So, what is elastic shortening loss? It is when a pre-stressing force is applied to a concrete member, the concrete shortens or compresses because of that force. Since the pre-stressing tendons are bonded to the concrete in the pre-tension members, they shorten together with the concrete that cause a reduction in the tendon stress. This reduction is called loss due to elastic shortening. So when does it occur? It happens immediately after the pre-stress is applied, that is during the transfer of pre-stress from the steel to the concrete. In the pre-tension beams, it happens at the time of cutting of the tendons when the pre-stress transfer to the concrete, while in the post-tension beams, it can occur gradually as each tendon is stressed. Loss due to elastic shortening. The concrete immediately shorten elastically when subjected to compression. The steel will generally shorten by a similar amount with a corresponding loss of pre-stress force. The formula for elastic losses, or P prime, is equal to P naught minus the loss in force. So this is the formula for corresponding stress in the concrete at the level of the tendon. First, for pre-tension members, it is the operation of pre-tensioning through various stages by animation. As you can see from the figure, shows the pre-tensioning of a member, which is beam, and then the figure below shows the length after elastic shortening of a pre-tension axial member. The slide also show the remaining how to find the formula for the remaining pre-stress force or P prime. Next is for post-tension members. It is a complete operation of post-tensioning through various stages by animation. The figure shows the post-tensioning of a member with a anchorage and duct jack, and then the figure below shows the length of tendon before stretching. The slide also provide the formula to find the remaining pre-stress force for the post-tensioning. In this slide shows one of the example for question regarding to loss due to elastic shortening of concrete. First, we extract out all the information from the question, and then we use the formula for pre-tensioning to find the remaining pre-stress force or P prime, and then the question wants to estimate the percentage loss, so we need to use the formula to find the loss of force due to elastic shortening, and then we can get the percentage losses, which is 5%.
Next is the immediate losses, frictional loss, that refers to the reduction pre-stress force along the length of the tendon caused by the frictional resistance between the tendon and its surrounding duct and shed as the tendon is stressed. So the tendon are placed inside ducts and sheds. If the cable is free, it is lost due to small misalignment, which is mobile impact, and if the cable is curved, it is a loss due to friction between tendon and so frictional loss happen when cables are stressed and they move inside the duct. Friction resists this movement and reduces pre-stress at points far from the jet. Bubble effect is a small random bands that cause extra friction, and the duct curvature design bands that increase friction with the duct. If you look at this diagram, the jacking end is where the tensioning force is applied. As we move along the tendon, the stress gradually decreases because friction increases. The more the tendon bends, the more friction we get, and therefore the more stress loss occur. This table shows the coefficient of friction, mu, for different type of duct and tendons. For example, steel ducts, HDPE ducts, and lubricated or unlubricated condition. A higher coefficient means more friction and greater loss. So, more bending, more friction, therefore more stress loss. As a result, the stress in the tendon decrease along it. So this is the formula for the wobble effect, which is Px equal to P naught e to the power of negative mu Kx, which is P naught is the jack force, and Px is the cable force at distance x from jack, and E is equal to lux 2.718, K is angular displacement per unit length, which is within 0.005 and less than 0.01 radians per meter, and mu is the coefficient of friction that we can go see at the table 5.1. Next is the duct curvature, which is the equation is Px equal to P naught e the power of negative mu theta, and theta is the sum of angular displacement over distance x. So this is the formula for the loss due to friction, which is P mu x equal to P maximum, which is maximum force, and multiplied by the 1 minus e the power of negative mu theta plus kx, which is e we can get from the table 5.1, and the value of x is the distance along the tendon from the point where the pre-stressing force is equal to P max.
Next, anchorage slip. Definition: a small distance of slip occurs at the anchorage device as the wedges or anchorage. Slip may vary from 2 mm to 5 mm. This slip causes a shortening tendon and reduce the effective pre-stressing force. How it occurs? The movement of anchorage block before it settles on concrete. The consequence: reduction in the tendon length. A definite total amount of shortening. Magnitude of slip can be known from the test or patterns of the anchorage system. Percentage loss is higher for shorter members. Next, in most post-tensioning system, when the cable is tensioned and the jack is released to transfer pre-stress to concrete, the wedges, wire, and slip over a small distance between the wedges. This is the mechanism of the anchorage cable. Next, Next, the magnitude of slip depends upon the type of wedges and the stress in the wires. The magnitude of loss of stress due to slip in anchorage can be calculated by using a formula which is for P over A equal to E S delta over L, where is the delta is slip of anchorage, the L length of cable, A represent for the cross-sectional area of the cable, E equal to modulus elastic of steel, and the last one is P is prestressing force in the cable.
What is concrete creep? Creep is a time-dependent increase in strain due to concrete under a constant stress, usually from safe weight, loads, or prestress. In other words, creep is the slow and continuous deformation of concrete under constant load. Imagine a concrete beam carrying a heavy load. Right after the loading, it deflects immediately. This is the elastic deformation phase. And over the time, it deflects more without increasing the load. That is the creep. So, why it happens? Concrete is not a perfectly elastic material. It has hydrated cement base, a gel-like structure with water-filled pores, and under sustained stress, moisture slowly moves within the concrete. Creep of concrete can be caused by age, which is younger concrete shows more creep because it's less stiff. Higher stress level can cause increasing creep. Denser concrete can cause less creep because of stronger aggregate and paste bone. Higher in cement content, water-cement ratio, and temperature can also increasing the creep. Stress losses due to concrete creep can be calculated by this formula, which will be needed the modulus of elasticity, stress in concrete at level of the steel, and specific creep strain. This is the extra information for the creep coefficient. What is shrinkage of concrete? Shrinkage is the reduction in concrete without external load, mainly due to the moisture loss or chemical changes during hydration. So, shrinkage is the time-dependent shortening of concrete due to drying and why it happens. After hardening, water pores of the cement evaporates the surrounding air. The loss of moisture also can cause the surface tension. These internal forces pull the solid particles closer and cause the concrete to shrink. Factors that are affecting the shrinkage of concrete: harder and denser aggregates like granite or basalt restrain shrinkage better, while lightweight aggregates allow more shrinkage because they have higher porosity. More water content means more water can evaporate later, causing a greater drying shrinkage. Shrinkage is the highest when the concrete is still young and not fully hardened. Thin sections dry faster and shrink more because moisture escapes quickly, and low humidity, which is dry air, increases the shrinkage because moisture evaporates. Loss of stress due to the shrinkage of concrete can be calculated using this formula, which will be needed total residual shrinkage strain, which is 3 times 10 to the power negative 4, and modulus of elasticity, just like this example 3.
Here, I will explain about the realization of steel in prestressed concrete. Realization is the reduction in stress with time under constant strain. In simple words, even though the steel is held at the same length, its internal stress slowly decreases over time. This happens because some of the elastic strain in the steel changes into inelastic strain, which causes a loss of the original prestressing force. There are a few main factors that affect how much realization occurs. Time. The longer the time, the more stress loss. Temperature. Higher temperature increases realization. Initial stress. Higher initial tension causes more realization. Type of steel. Low realization steel can reduce this effect. According to Eurocode section 3.3.2.7, realization is usually measured over 1000 hours. Typically, the initial stress is around 70% of the steel's characteristic strength, and the losses range between 4% to 10% of the pre-stress force after transfer. Next, this is loss due to time-dependent equation. This long equation here is used to calculate the total pre-stress loss caused by those three effects combined: creep and shrinkage of concrete and realization of steel. In this slide, it shows the meaning of each symbol or letter in the equation, so we can understand what each term represents in the calculation. This slide shows an example of estimating the pre-stress losses at midspan for a post-tension beam. Here, the beam is stressed by two tendons with a parabolic profile, and all the data given such as the pre-stress force, modulus of elasticity, creep coefficient, and shrinkage strain are used to calculate the total losses. The next three slides will show the calculation steps to determine the pre-stress losses starting from friction loss to realization loss.